Hello everyone, I'm Mehmet Kerim, and I'm pleased to present our work Red Carpet to Fight Club, partially supervised domain transfer for face recognition in violent videos. This is a joint work with Yunuscan Bilge, Nazlı İkizler Cimbiş, and Pınar Duygulu from Hacettepe University, and Ramazan Gökberk Cimbiş from Middle East Technical University. In many real-world problems, a domain discrepancy between training and deployment data is observed. A prime example is violence videos, where suspects expose a diverse set of facial expressions and poses, but need to be identified based on their clean photos. Moreover, some people may not have prior records. We formulate this problem as a partially supervised domain transfer problem, where the goal is to transfer the recognition model trained on clean images to the target domain of violent videos, where training videos are available for only a subset of subjects. First, in order to create a testbed for our problem, we introduced the WildestFaces Dataset. WildestFaces is formed of violent movie scenes collected from YouTube and has various conditions at their extreme. As shown in the plots, it has various blur levels, face scales, poses, and a large per actor age variance. For the clean domain, we curate a new dataset from IMDb Wiki and complement it to compass all actors of WildestFaces dataset. Dataset splits are designed to reflect our proposed problem. The entire IMDb dataset is used to train the classifier to be transferred. During domain transfer, we use videos of 40 actors in WildestFaces, same 40 and unseen 10 actors for validation, and the entire actors for testing. This setting closely follows a generalized zero-shot learning framework, where a model is optimized to recognize both seen and unseen classes. Here, we formulate our partially supervised domain transfer problem. We first train a source domain classifier, denoted by W, with clean images of IMDb using VGG features, denoted by phi-xi. The aim is to learn a transformation that transforms the representations of target domain to be compatible with the source domain classifier. We divide the transformation into two parts: classifier transfer, denoted by tau, and temporal adaptation, denoted by psi. First, we focus on the classifier transfer. We consider several alternatives, such as a simple, fully connected layer and other domain adaptation baselines. We observe poor results due to a combination of limited data and high complexity nature of FSC layers. Assuming source and target domain representations are sufficiently correlated, we then consider a low complexity alternative called affine classifier transfer that performs an affine transformation, denoted by alpha and beta. We then extend this affine transformation by stacking multiple instances of it with residual connections. Since our problem is an instance of video to image recognition, we evaluate several temporal aggregation methods. Keeping in mind that our videos are exposed to severe blur, non-stationary expressions, poses, and noise, we consider a temporal adaptation method that implicitly takes into account the latent factors in the videos. To this end, we propose the attentive temporal pooling mechanism. Attentive temporal pooling mechanism attends to informative parts of a sequence in a learnable fashion. As baselines, we compared with average max pooling and other baseline methods. Comparison of different classifier transfer layer alternatives are shown in the plot. As previously mentioned, fully connected layers perform poorly. Two domain adaptation baselines, MMD and ADA, perform better when they're implemented with the affine transfer layers. Our proposed affine layer performs best among all alternatives. Comparison of different temporal adaptation approaches are shown in the plot. The results verify the efficacy of affine transfer layer across all temporal adaptation methods. Moreover, attentive temporal pooling is visibly the best alternative among strong baselines. We also fine-tune the source classifier with WildestFaces training set. Residual stacked affine layer is the best option among all alternatives. We finally analyze the combined effect of our proposed methods. When compared to a strong baseline and a self-attention-based approach, our residual stacked affine transfer module with attentive temporal pooling introduces clear improvements in the final result. Here, we can see example sequences where each frame's attention score is shown above frames. Our proposed approach learns to attend to images with less blur and informative poses. Thanks for watching our presentation, and feel free to reach out for questions. Our dataset is available at our project page.